Page 1 of Math Induction, Chapter 9. The process of induction, page 276, reading. Math induction is examining specific cases in order to formulate a general conclusion. A statement we believe to be true is called a conjecture or proposition. So let's look at the first problem. It says to copy and complete a conjecture. The nth term of the sequence 3, 7, 11, 15, 19 is blank for n is an element of something. Okay, so this looks like a sequence. Let's see what kind of sequence it is. I can see that the intervals in between here are regular intervals. Seem to always be plus 4, plus 4, plus 4, right? So we call this an arithmetic sequence, right? So if you remember, the equation for an arithmetic sequence term is u subscript n is equal to u subscript 1 plus n minus 1 times d. And here d is 4 because there's a space between each set of numbers. It's 4 units. So we could say that the first unit is 3. N minus 1 times 4. So that's how we find the nth term of the sequence. If we want to simplify it, we could write 3 plus 4n minus 4, which is equal to negative 1 plus 4n. Okay. Now let's look at what we need to fill in here. So the nth term of the sequence is negative 1 plus 4n, or 4n minus 1. 4n is an element of let's see, we're going to start with n equals 1 in order to generate the first term. So that means n is basically greater than or equal to 1. One compact way to write that is we could write that it's n is an element of the positive integers. And that's basically the same thing as writing that. Okay, z is these integers, whole numbers. 2, examine the following using substitutions like equals 1, 2, 3, 4, hence complete the proposition or conjecture. Okay, so here we have a conjecture that 3 to the nth is greater than the expression 1 plus 2n. So let's test that out using different indexes. So let's test it out using n equals 1, n equals 2, n equals 3, and n equals 4. So if we put in n equals 1, we'll have 3 to the first is greater than 1 plus 2. So is 3 to the first greater than 3? No, it's not, right? Let's try the next one. 3 squared is greater than 1 plus 2 times 2, which is equal to 9 is greater than 1 plus 4, which is 5. Is that true? Yes, it is. Let's try another one. 3 cubed is greater than 1 plus 2 times 3, which is the same thing as 27 is greater than 1 plus 6, which is 7. So is that true? Yes, it is. Last one. 3 to the fourth is greater than 1 plus 2 times 4. That's equal to 81 is greater than 9. Is that true? Yes. Okay. So it looks like the trend is that like every step it's getting a little bit bigger every time. The right side, right? The right side gets a little bit bigger every time. The left side gets very quickly bigger and bigger. So it looks like the trend is that if we get bigger and bigger values of n's, the left side is definitely going to be greater than the right side. So only on the first example, which is n equals 1, is 3 to the n not bigger than 1 plus 2n. Okay, so let's say that this is true for n is a positive integer where n is greater than or equal to 2. Let's move on to C. So now we've got 7 to the nth plus 2 is divisible by something for certain numbers. Okay, so let's try that out again. We're going to try out n equals 1, 2, 3, and 4. let's try 7 to the first plus 2, which is 9. Is it divisible by a certain number? And let's just do a bunch of these and see before we actually test to see if it's divisible by a certain number, shall we? 7 to the third plus 2 equals, so 7 times 7 times 7 is 49 times 7, which is 343 plus 2, which is 345. And then 7 to the fourth plus 2 is equal to 2403. And do you know the trick that if you add the digits to a number up, if you get a number that's divisible by 3, the number is divisible by 3? So you can tell even with this one, if you add 2 plus 4 plus 3, you get 9, which is divisible by 3. If the digits added together are divisible by 3, then the number itself is divisible by 3. So all these numbers here are divisible by 3. For n is an element of positive integers, and n is greater than or equal to 1. Okay? All right. Number 3. Copy and complete each of the following conjectures and then write it using summation notation. So we are going to add together 2 plus 4 plus 6 plus 8 plus 10 plus all the way up to 2n. So the first thing they want to do is express this in summation notation. Do you remember summation notation? So we're going to have sigma of the index is equal to 1 to n. And then inside here, we're going to put the term in terms of n, which is 2n, obviously, or 2I in this case, right? And so if we put it in a summation where we start with the index 1 and go all the way to n, you can see that like the first term is going to be 2 times 1, second term is going to be 2 times 2, 2 times 3, and the last term is going to be 2 times n, right? Okay, so that works out to be exactly this sequence. All right, now let's see, what are we going to do with our summation? So if we have a bunch of multiples of 2 added together, would this be a sequence that we already know how to add up? Well, basically this is like a arithmetic sequence, isn't it? Because the first term is 2, and then each term is separated by 2 to the other term. So we could say that this is an arithmetic sequence where the first term is 2, and the distance between each term is 2 also. Okay, so if we have this, we can confirm that this is indeed the right formula by expanding. So do you see how it's 2 minus 2 and you just end up with 2n? Okay, so this is an arithmetic sequence. And if you remember, the sum of an arithmetic sequence can be found by this formula here. Okay, so u1 in this case is 2, and then un in this case is 2n. So let's rewrite it again. N divided by 2, 2 plus 2n. And then let's distribute the 1/2, and we'll end up with n. We'll distribute the n also. So we'll get n plus n squared, or n times n plus 1. Okay, either one of these is fine. Okay, so you could say that if you add up this sum, you should get n times n plus 1. Okay, so we know that it's equal to n times n plus 1 for, n is a positive integer, where n is greater than or equal to 0, greater than or equal to 1 maybe. Let's see if this works. So like if you put, if you just have the first term only, it would be 2 is equal to 1 times 1 plus 1, which is 2. So that works, right? If you had 2 plus 4, then you have n, which is 2. times 2 plus 1, which is 6, and that works also. What if we had 2 plus 4 plus 6? So in this case, of course, this is n equals 1, and this is the case where n equals 2, and this is the case where n equals 3. When n equals 3, we have 3 times 3 plus 1, which is 3 times 4, which is 12, and that is indeed equal to 12. In the last case, we'll do n equals 4. n equals 4 would be 2 plus 4 plus 6 plus 8, which is equal to 4 times 4 plus 1, which is equal to 20. And we can confirm that this added together is also 20. Okay? So it seems that n is greater than or equal to 1 is what we would put here. Okay? Okay, now we got this interesting looking sequence here. Let's try to expand this. Maybe it'll help us figure out what's going on here. So instead of factorial, let's actually write out the number that the factorial is. So we'll have 1/2, because 1 over 2 factorial is actually 1/2. We'll have 2 over, and 3 factorial will be 3 times 2 times 1, which is 6. We'll have 3 over 4 factorial. 4 factorial is 3 factorial times 4, which would be 4 times 6, which would be 24. And then we'd have 4 divided by 5 times 24, which will be 120. And that will be added all up until we get to n over n plus 1 factorial. Okay. So let's start testing out what happens if n equals 1, for example. If n equals 1, then we would just have the first term here. So we would have 1/2, right? And so then the sum would be 1/2. And what about when n equals 2? When n equals 2, we're going to have the first two terms, which would be 1/2 plus 2/6. And we could add these together if we make a common denominator of 6, I mean. So we would get 5/6. That would be the answer for n equals 2. For n equals 3, we're going to have the first 3 here. So it'll be 1/2 plus 2/6 plus 3 over 24. We could put them over a common denominator. We get 12 over 24 plus 2 over 6 is equivalent to 8 over 24 and 3 over 24. And if we add the numerators together here, we get 23 over 24. Now we're going to start seeing a pattern, right? Because you see how 1 over 2, 1 is 1 less than 2. And 5 over 6, 5 is 1 less than 6. And finally, 23 over 24, 23 is 1 less than 24. Let's try n equals 4 finally. So now we're going to have 1/2 plus 2/6 plus 3 over 24 plus 4 over 120. Now to add these in the common denominator, we would put everything over 120. First one would be 60. Second one would be 40 over 120. And the next one would be 15 over 120. And the last one would be 4 over 120. And if you add these up, it would be about 119. Oh, 119 over 120. What a coincidence. Once again, the rule is that the numerator is 1 less than the denominator. So now we can kind of like write down a rule for this, which would be that the denominator is going to be the same as the denominator of the last fraction, and then the numerator is going to be n plus 1 factorial, which is the denominator, minus 1. Okay, so let's write that here. So the numerator is going to be n plus 1 factorial minus 1. The denominator is going to be n plus 1 factorial. And that is going to be true for starting with n equals 1. So we're going to put that n is an element of the positive integers and n is greater than or equal to 1. One thing I forgot to write here is the summation notation, which they asked us to do. In this case, the summation notation would be very similar to this one. So it would be the sum of the index I equals 1 to n, because we're talking about starting n out as 1. And then we're just going to put that expression there with i's in it. I over I plus 1 factorial. And this, of course, is equal to this here, right? So it's going to be equal to n plus 1 factorial minus 1 divided by n plus 1 factorial. Okay? All right, that's it for this page.